Professor Asali could not be here. She's might have COVID, hopefully not. So the first talk is going to be given by, so we're going to shift everything by 30 minutes. So the first talk is going to be given by Gustavo Dalpian, and the title is Materials Informatics, Current Trends and a Few Examples.
Okay, good afternoon, everyone. Can you hear me? Yes, it's what? Is it working? Closer? Okay, can you?
Try now.
Okay, better now? Okay, so I would like first to thank the organizers for inviting me to come here. It's very, very nice. I really enjoyed this kind of meeting. We have a time to talk to colleagues and see people that we haven't seen for a long time. So I think this is kind of ideal type of conference for interactions, okay? So today I'm going to tell you a story or to show you what I believe are some new trends in this field of materials simulation or computational modeling of materials. And I'm going to show you a few examples of what we've been doing in this field, okay? So I will start with this slide here, okay? So I've taken this slide from my PhD thesis that I finished at the Physics Institute in 2003, okay? Actually, this is the band structure of silicon. So this is very simple, right? And actually, I calculated it during my master, but at the end, I realized that it just appeared in my PhD thesis. And Pedro Venezuela here taught me how to do this kind of calculations. And you know, we use density functional theory to do that. And when I finished this calculation and plot this band structure, I have to tell you that I was very proud of myself, okay? So, because it was so hard to do these calculations, you know, softwares, they were not friendly. You had hundreds of parameters to test. And Marilla was the director of the supercomputing center by that time. And we had to use supercomputers. And so it was a mess, okay? It was very hard. And that's why, after plotting this band structure, I was very proud. Some of the first results I've obtained by that time. The point is, nowadays, I have an undergrad student who left physics undergrad from UFABC. He finished his undergrad and went to a master in Switzerland. And during his Iniciação Científica undergraduate studies, he plotted automatically the band structure of 2,000 two-dimensional materials with one click, okay? So what I want to tell you today is that the area or this field of how to simulate materials from a initial perspective, it changed a lot over the last 2 decades, okay? And I would like to tell you or show you what are these current trends and what we've been doing in this area. I think everything started with this Materials Genome Initiative launched by President Obama in 2011, okay? So the idea was to use computers to simulate materials in a more in a smarter way or in a high throughput way. So the idea is that the methodology after this time, after that band structure, the methodology was mature, okay? So and the softwares, they were also advanced a lot and they were very friendly to deal and to make calculations. And the number of errors in these calculations were only intrinsic of the methodology itself, but you didn't have computer errors anymore and things like that. Okay, also computers advanced a lot, and people thought, okay, now we can do more with this methodology that we have. Instead of plotting the band structure of one material like silicon, people said, let's plot the band structure of all materials in an automatic way. And that's what they did. Okay? So the idea of this materials genome was to simulate in an ab initio fashion all the materials that were synthesized before and characterized by X-ray diffraction data, okay? And the idea was to put all the simulations in public repositories that you only go there, you select your material, and you get all the information that you want, okay? And, oops. And so here I'm showing you, this is a paper published some years ago that talks about these materials repositories and materials databases and show what are the main materials databases. And this is an important trend and an important tool for us to study materials nowadays. Okay, so here we have some important things. Actually, I put here Landau Borstate. So this paper only showed this timeline here. But as everyone here is from condensed matter physics, I think everyone held these Landau Borstate books before. So they were way before these guys, right? So we already had databases before. Okay, but these are some important milestones. Here you have ICSD. It's inorganic crystal structure database. Basically, the idea is that all materials that are synthesized experimentally and characterized by X-ray diffraction, people put the CIF files, the structure of these materials into this database. This is a paid database, okay? And then a few years later, here, where is in materials project, so this is a team from MIT and Berkeley, and they use some robots to simulate all the materials that were on ICSD, okay? So now we have on materials project, you can enter this website and you have all the synthesized materials simulated from an ab initio perspective, okay? The idea, another interesting point is that we can even grow beyond what experimental databases. So we can populate these databases with materials that have not been synthesized yet, okay? This is a good point about simulations, right? Computer accepts everything. So you just throw the numbers into the computer and it will give you a result. Okay, and you can simulate materials that don't exist yet. So we are doing this, for instance, for this Jacobsonite. This is just an example. It's calcium aluminum fluoride 5. Okay, this is a known material. And then we can expand this family of material, simulating some different compounds. So instead of calcium, we can put magnesium, strontium, barium. Okay? Instead of fluoride, you can put chloride, bromide, iodines, and so on. So you can make a lot of materials that have not been synthesized yet, but you can get information through simulations. Then we can increase these theoretical databases through this kind of fashion. So these are DFT databases, for instance. These red ones are the known materials from ICSD, and we simulate a lot more of materials, huge databases with hundreds of thousands of materials simulated. Not all of them are stable, right? We can calculate the stability of these materials through some diagrams, such as this one that we call convex hull, okay? And then we can learn whether the specific material would like to be stable. If it's in the convex hull, it will be stable. If it's not in the convex hull, it will like to phase separate into other materials. So we can calculate this, and then we increase a lot these databases, and we can suggest experimentalists to go after some materials that we think are stable, okay? So once we have this tool, huge databases of materials, hundreds of thousands of calculations, millions of properties calculated, we can switch the way we study materials. Usually what we did, the traditional method, this is a slide that I borrowed from my friend Alex Zunger, and he has this inverse design idea. So the traditional method that is usually we see very often is the following. Let's choose a material, silicon, like I said. Then I simulate it, and I look at its properties, and then we ask ourselves, okay, where can we use this silicon? Okay? So this is the traditional method that people use to study materials. Now, as we have a huge database of materials with hundreds of properties calculated, we invert the idea. We go to experimentalists or to some people making devices or anything like that, and we ask ourselves, what property do we want, okay? And then we first ask what property, then what you want, and then you go to the database supermarket, and then you go to the corridors and choose the material that fits the property that you want, okay? So this is what we call inverse design of materials. We first define the property, and then we look for the material that fits this property. Okay, so here in our group at UFABC, we decided to enter this fashion, but we were interested in some properties related to spintronics or spin-related phenomena. That's why I was talking to Dario to try to understand his spin splittings before, okay? Our spin splittings are a little bit different, okay? We would like to understand spin-related phenomena, and I can tell you, okay, we can apply this these materials with some spin splittings into some spintronic transistors. This is very hot, okay? This is a very hot topic, lots of papers published every year. But I like to say, oh, you know, the properties of these materials are so cool that I like to study them just because they are so nice and they have so many unusual properties, and let's go in that direction, okay? So the idea, it would be to ask yourself, okay, we want to study two-dimensional materials, and we would like some materials with some specific spin splitting. What is the best material to fit these spintronic properties, okay? So this is the question that we wanted to ask. And in order for us to answer this question, we decided to calculate this spin splitting of all two-dimensional materials. And that's what we did. We published this paper in this year. Oh, there is no reference. Okay, so this is a journal from the Nature group. It's called Scientific Data. It's a different journal, different kind of journal. It's a journal focused on databases, okay, any kind of databases. And so they say, oh, you don't have a scientific result in this to publish paper, but we went beyond, and this is the undergraduate student that made the calculations. And we have a paper on arXiv, and he inserted all the band structures. So the paper has 506 pages, so with all these band structures, okay? So the idea is the following, and this is why I was asking Dario. When you have a standard semiconductor, you have a band structure like this, okay? This is a parabolic band. This is you have your reciprocal space. Two-dimensional space. And here is energy in the other direction, okay? So this is your dispersion relation for a standard semiconductor, okay? And when you have standard semiconductors, spin up and spin down bands are degenerated, okay? This degeneracy comes from two kinds of symmetry. Let's say you have time reversal symmetry and inversion symmetry. And whenever you break some of these symmetries, you can split the spin degeneracy of these bands, okay? So when you break time reversal symmetry, like applying a magnetic field, you see you have something similar to a Zeeman effect, and you have a spin up band here and spin down band here. When you break inversion symmetry, we have what we call Rashba spin splitting, okay? It's a little bit more complex spin texture that you get, but you also break the degeneracy of these bands. So every time you break some kind of symmetry, you break the degeneracy of these bands, and the result is some kind of spin splitting, okay? This is not a new idea, okay? This is not new. So I think the first time this was reported was in 1955. This is a paper by Jean Dresselius. Jean Dresselius was the husband of Mildred Dresselius from the carbon nanotubes. She came to Brazil many times. Many of you might know her. So Jean was her husband. Okay, and he reported, he made some tight binding models to understand spin splitting in zinc blende semiconductors. Okay, but well, when we have, so what I've told you so far is when you break some kind of symmetry in your material, you can have some different spin splittings in your band structure. Okay. And you can have several different types of spin splittings. Depending on the physical properties of the material that you have, you might have different kinds of symmetry breakings and bands, okay? So what we did is the following. We determined different, what we call design principles to get these spin splittings in these materials. Design principles are very important in this data science field, okay? So you have to search for design principles are physical properties that have to be followed in order to get a specific property. So we can track in a huge database, we go after these design principles and we will search or we will find a material with a specific property, okay? So in order for you to have this kind of spin splitting, you must have, first, you need a large spin orbit coupling in the atoms that this material is composed of, okay? And you need non-central symmetric structure. Then you might have either the structure has an intrinsic electric dipole or the K point where the spin splitting occurs is a time reversal invariant K point. Or there are discussions about the Hamiltonian that you can get. And depending on whether you check this physical property or not, you will get Rashba spin splitting, Dresselius spin splitting, Zeeman spin splitting. And this high order, we invented this high order, okay? So if you go to the literature, you will not find the referee complain about this. But we couldn't fit it into the other types, so we decided to create a new one here that we call high order, okay? So once we have these design principles, we can we can go to our database that we have calculated all the spin splittings, all the materials using ab initio methods, okay? And we go to something like this and we start doing some filterings and for some searchings in order to get these materials, okay? So we used VASP, and this is not very important, but we did more than 1,300 calculations for these materials. We started from this C2DB, is a database of 2D materials, specific database of 2D materials, okay? We made some filters. We wanted to search for material, only semiconductors, materials that were non-central symmetric, non-magnetic. And so this is what we call enabling general design principles. And these are unique design principles that we classify these materials into Rashba, Dresselius, Zeeman, or high order, okay? At the end, we got 205, and these numbers of materials that had this kind of spin splitting in our database, okay? So this is automatically done in our scripts. So this is the algorithm that this student designed. So you do the calculation, you just provide the band structure to this script. It's available on our GitHub, the GitHub from our group. And it does these filters, and at the end, the script, only looking at the band structure, it will tell you whether your material is Rashba, Dresselius, Zeeman, or high order. So they do this automatically, okay? And what we did then was, here are just a few examples. So these are band structures of these 2D materials, okay? Here, just to show a Rashba spin splitting, red is spin up, blue is spin down, okay? And then you observe these bands are not degenerate anymore, they are spin split, and this is what we are looking for. So this is the signature of Rashba. This is the signature of Dresselaus. This is the signature of Zeeman, and this we didn't know how to classify it. We called it high order. So once we have this, before I tell you this, so all these calculations that we did, no, let me go one, no. Once we have all these results, we generated some different analyses and databases. So all our calculations, everything is available, publicly available. So all the calculations were inserted into Nomad, that is an European repository. Matthias Scheffler and Claudia Drexel take care of this one. Okay. We have this archive file with 500 pages that people can go and look for the band structure. We have tables for you to look, and we have these MongoDB databases for you to search inside. If you are more into data science, you can go into these databases. Okay, so everything is available in this materials cloud. Okay, so once we have done all these calculations, all the calculations are available, we can start playing with this. We can ask ourselves, for instance, what are the materials that maximize rush by spin splitting, for instance, okay? So that's what we did. We ask ourselves, it's Zeeman spin splitting. So we wanted to ask what materials maximize Zeeman spin splitting. And we used, I think I would not have time enough to show you everything, but we used Bayesian theory to search for the compounds that have higher probability of showing a large Zeeman spin splitting, okay? I will not have time to go through this, but we use we do some machine learning. We have to tell machine learning what the materials we are looking for are. So for each material, we have to build large vectors where we tell that are basically composed. So this is composition, for instance. So molybdenum disulfide. So you have one position for each atom from the periodic table. So it's false, false, false. When you get to molybdenum position, you put true and continue, so on. Okay. We have to do to build some descriptors for structure as well. This is much more difficult. Okay, but there are some graph. We use some graph theory to work on describing this kind of guys, but I'll have to skip. And at the end, we get we can get what are the atoms that maximize Zeeman spin splitting, what are the crystal structures that maximize Zeeman spin splitting. And looking at this, we can retrofeed our model and simulate new materials that were not in our initial database to see whether what we've learned does work or not. And we've learned that it does work. And we can suggest, for instance, a new material that didn't exist before with a maximized spin splitting, okay? So this is iridium tellurium iodine in a Janus structure. Pedro Venezuela knows very well the Janus structures. And this one should have a very large spin splitting. Alexandre, how is my time? 5 minutes. 5 minutes, okay. Okay, so there is a lot of space for, there are a lot of databases around, okay? Computational databases around. So Materials Project, Nomad. But I think there is still space for focused databases, okay? So if you want to search for a specific property, I think there is still space for building property-specific databases, as we did with these spin splittings. There are databases of halide perovskites and so on. So I think there is still space for this. Okay. So we have another study that I'll go very fast through this one that also uses machine learning to study materials. Okay. So we wanted to use machine learning to understand magnetic ordering into the materials. Okay. This is kind of a new subject because if you look, I was talking to Eduardo yesterday, actually. So there is a paper from Mermin and Wagner and Mermin, exactly, from 19 70-something that said that you shouldn't have magnetism in 2D materials, okay? But, you don't have magnetism in 2D materials until someone observed it, right? And that's what people did. So there are many papers here, nanoletters, very fancy papers, actually, Natures, and so they observed some ferromagnetism, anti-ferromagnetism in these 2D materials, okay? People don't understand very well what's going on, okay? So we decided to study this magnetism in these 2D materials using machine learning. And what we wanted to do was something similar to this. This is not my drawing, okay, but this is what people understand more or less. It doesn't mean a specific rule, but it wants to show what are the trends for exchange interactions in 3D materials. So usually, if the system is metallic, you have either indirect exchange or itinerant exchange. If it's non-metallic, direct exchange is super exchange. If you have 3D transition metals, is well, these two. So this is not a rule. This is just some general observations. And machine learning can do or can get general trends as these ones. And that's what we wanted to do with these 2D materials, okay? We used this machine learning. So we did two different studies. We got a database of ab initio calculations of magnetic states in 2D materials, okay? And first, we wanted to separate, to run machine learning to separate magnetic from non-magnetic. Non-magnetic is diamagnetic. From materials, okay? And then on a step 2, we wanted to construct a model that would separate ferromagnetic and anti-ferromagnetic materials, okay? This database, it has more than 1,000 non-magnetic materials and 400 magnetic ones. We did the same machine learning that I've told you before. I'm not getting into the details. And at the end, we got this. This is a confusion matrix. Oh, my time is over. So, well, the model was very good. Okay, more than 80% getting the correct answer. And we can get some trends using this SHAP analysis. This is an analysis in order to get some interpretability of your machine learning. This is very important. And we've learned, for instance, that the presence of iron is important to classify a material as magnetic. This is not very, so this is right. But that's what it's correct. Machine learning is getting the correct trend, right? So we were very happy. So we can get some other trends here that I'm going to skip, okay? And for getting ferromagnetic and anti-ferromagnetic, we had to change methodology. So this is CISO approach, also from Matthias Scheffler. And this is much more delicate, much more complex. But in principle, we could get a model with around 80-something% efficiency, okay? Here for the magnetic things, we were able to study this and learn some new stories. And well, just to thank the guys here that did this work. And just to then, thank you. Obrigado, pessoal.
So we have time for a couple of quick questions.
I have one broad, maybe naive question about the general machine learning approach. I've been hearing that usually machine learning is good for kind of interpolating instead of extrapolating, in the sense that you can find a material with a property that is within the database somehow, but it's not so good to go beyond what is inside the database or something like that. Is that an approach or a research avenue for treating those cases that are extrapolating in some sense?
Yeah, this is a very good point. And I think that it's not a trend, but it's something that we should take care when we do machine learning, okay? So when you want to extrapolate your data, you have to be sure, like we were talking with Maurice this morning, you have to be sure you are training your model in a proper way to get properties that it's trained for. So it's very hard for you to think that you are going to train a model that is going to learn something it was not trained for. Okay, so silicon, for instance, they trained phase diagram of silicon in 6 different structural phases, and they trained machine learning to learn that. And then they used another phase of silicon that you see, they asked, oh, would this be stable or somehow energy? And machine learning couldn't get the answer because it was not trained for that, okay? So I would say machine learning is very, very powerful. There are many, many, many different recipes and flavors and ways of doing that, okay? You have to take care. It's very powerful, but you have to ask this question that you ask now before starting going to conclusions, okay?
I would like to see your results for these two-dimensional materials.
For what? Sorry.
For the two-dimensional materials. We know for sure that materials which are isotropic from the magnetic point of view, they don't have ferromagnetism. They are isotropic. This is the theorem of Mermin and Wagner, which applies to true Heisenberg models or XY models, things like that. On the other hand, if you have an isotropy, a certain degree of anisotropy, you may order the two-dimensional Ising model is ferromagnetic. So I would like to see whether this is the trend of the results. Okay, I would like to see that.
This is a very good question. We could ask ourselves about and look in our database to see if we get something like that. But usually the material is not exactly 2D. You see that this is 3 layers and so on. So you get out of, so maybe even graphene has some ripples, you know, that would stabilize. But you're correct. This would be actually very interesting when we could look in our database to see if we can get some trends like that.
Any further questions? So if not, let's thank Gustavo and move. Oh, sorry.
So in this case, you're looking at a single property, right? So how would you go about trying to find structures which have certain combinations of properties? So not only certain spin properties, but something like elastic constants or something like that. So how would you go about that?
So then one way, there is not only one way to solve this kind of issues. I think one way using Bayesian inference, okay? So Bayesian inference is a way to calculate, to update probabilities when you give some further information regarding your system, okay? So, well, you use this kind of methodology here. I've skipped it, but we use this. For instance, the probability of having a Zeeman spin splitting larger than 0.1 eV is 0.22 in the whole database. And then you ask yourself, what if you have bismuth in the material? Then you update using Bayesian inference, you update your probability, and the probability goes to 51%, okay? So you can update probabilities. I think this is a good way to go after your question. Exactly.
Okay, so let's move on. Thank Gustavo again. The next speaker is Marília Caldas.
Eu tenho que tirar esse aqui.
É esse aqui.
Você pôs em cima do meu.
Tem um